Hello everyone, how are you? How's everything? I hope everything is going well. Today I'm going to tell you about the applying the MOSFET in amplifier design. If you remember, in the beginning that we started to talk about the transistors, we talked about the BJT, then we learned how to analyze BJT in DC, and then we learned the amplifier application of the BJT. And now we're doing the same thing about the MOSFET. In the previous session, we learned about the MOSFETs and we learned how to run a DC analysis on MOSFETs and how to find ID. Today, we're learning how to apply MOSFETs in amplifier design. And as you remember from the previous session, this amplifier design by MOSFET, we can also call it AC analysis of MOSFET or a small signal analysis of MOSFET. I use the reference to the BJT a lot now because you know that one, so you will learn this one much easier by comparison. For example, over there you remember that the BJT can be used as an amplifier only and only if it is in the active mode. For the MOSFET, this scenario changes. It only works as an amplifier if and only if it is in the saturation mode. I remind you how we used to find the status and the mode of the operation of the MOSFETs. You remember this from the last session? We check VGS, the voltage between the gate and the source. If the voltage between the gate and the source was smaller than the threshold, then we're in the cutoff. If it was greater or equal, then we check the VDS, the voltage between the drain and the source. If the voltage between the drain and the source was smaller than VGS minus the V of threshold, we're in the triad region. It's like the active region in the BJT. If the VDS was greater than VGS minus VTN, then we're in the saturation. And this is the mode that we can use the MOSFET as an amplifier. Here in this picture over here, you can almost tell that this is the only region that VDS is changing significantly with the change of VGS. That's why you can have an amplification. It means a change in the gate source voltage can result in a bigger change in drain source voltage. So it can be a voltage controlled voltage source, right? So in the BJT, it could work for us as a current source, right? So here we can kind of have a voltage amplifier. So we're gonna continue to see that how to analyze it in AC. So in this case, this scenario that we only had one DC source here in the gate is not going to be the case. We're going to have an AC source here as well. So we will have a shape like this one. Look, we have a DC source. As you remember, I told you the DC source, we show it usually with the capital letters. The AC source, we show it with the small letters. So this one with the capital letters is the DC source. Then this VGS with the small letters is the AC source here. So what we want to do, we want to amplify this voltage here by the use of this MOSFET in the saturation mode. And what I was telling you over there, you can see it here. Small change in VGS can result in a big change in VDS. So you can tell, you can see the amplification in this graph. So how to do that? The process is very similar to what we were doing over there. Over there, we used to find IC, used to do the DC analysis, find IC and find GM, right? It's the same here. So first, you will forget about the AC source. So you will imagine that it's not there. You will imagine it's like this. There's just a DC. So you will do your normal analysis, normal DC analysis, and you will find ID. You remember how, right? I just remind you again. ID, when you're in the saturation mode, ID will be this value, 1 over 2 Kn W over L VGS minus VTN square. So I told you, don't look at the complicated looking shape of the formula. It's actually pretty simple. All of these things must be given to us. So we short circuit the AC source. Let's go back to the shape. So we short circuit this one, so we'll have this, right? Then we will figure out, first of all, we have to make sure we're in the saturation mode. After we make sure that we're in the saturation mode, we find ID using the formula that we just talked about. After you found ID, then you need to find GM. What is GM? GM is actually ID over VGS, but you don't need to do this operation. It's simply this one. It's going to be K prime W over L VGS minus VT. Everything you're going to have. You're going to have everything. So GM will be simply W over L VGS minus VT. So you're not even using the ID that you found. You just find ID just to make sure that you were in your saturation mode. Even that one you can tell by checking the condition, checking the condition that we mentioned over here, that you just check this to make sure that VDS is greater than VGS minus VTN. Then you can tell that yes, I'm in the saturation mode, the saturation region. Then you will come here and you find your GM using this formula, K prime W over L VGS minus VT. After you found your GM, you simply replace your MOSFET with this circuit. Look, again, it's very similar to what we were doing in the BJT with one difference. Over there, you used to have a resistor here. You used to call it R pi. Between the base and the emitter, you used to have a resistor. Here, you have nothing. It's like an open circuit with the voltage of VGS. Do you know why? Because in MOSFETs, the gate does not draw any current. The current at the gate is 0. So you can tell, look, here if you had even a 1000 kilo ohm of resistor, you wouldn't care because there is no current in the gate. So there will be no voltage drop here. So whatever the voltage is here, we will have it right at the gate. So this makes the analysis of the MOSFET much easier. Look, there are some cases that you might see in the questions that gate and the drain are connected to each other using a resistor, okay? But you don't need to worry about anything since the gate does not draw any current. This resistor will be irrelevant here. It means the current ID is not going to be divided between this branch and this one. Everything is going to go through. That's why ID and IS are always equal. Unlike BJT, that the emitter current was IC plus IB, here in MOSFETs, the current in the drain and the current in the source are equal, because gate simply has no current. So that is why in your model here you don't have a resistor here. So whatever the voltage is here is gonna be here. So again, it's one of the other things that makes even the AC analysis of the MOSFET much easier. Now, between the drain and the source, you will have a current source, as you expect. The value of this current source will be GM times VGS GM times whatever the voltage is here. So, what is GM? Is this. GM is K prime N W over L VGS minus VT. This is super simple. And exactly like what you saw in the BJT, we have two different types to model. We have the pi model and we have the T model. Here's the T model. You can use either of these models interchangeably when you want to do the AC analysis of the MOSFET. So I recommend you, like the case in the BJT, I recommend you to use this shape for analyzing the pi model for AC analysis of the MOSFET. So as we said, GM is simply K prime of N W over L VGS minus VT, as simple as that, which will be, if you put it in the formula, which will be equal to 2ID over VGS minus VT, right? Which formula? Just show you this formula that we talked here, right? So to put this, take 2 to the other side, it's going to be 2VT, right? And remove one of this VGS minus VT and bring it to the denominator. It's going to give you the description of the GM. So this is actually this 2ID over VGS minus VT is exactly KW over L VGS minus VT. Again, I repeat this, don't worry about the fact that the formulas might look a little bit complicated. It's actually the simplest thing in the world to do the analysis of the MOSFET. It is a very advanced and cool and edge of the technology of the advancement in the electronics, but thank God on the paper the analysis is not too complicated, and you just need to be familiar with the terms in general. So this is the width in the semiconductor, this is the length, this is the voltage between the gate and the source, T is the threshold voltage, this K is a constant that we had explained a little bit where it's coming from, but when it comes to problem solving, all of them are given to you. So let's review together. First, we do the DC analysis. We remove all AC sources. If there was a voltage source, we short circuit it. If there was a current source, we open circuit. Then, if there are capacitors, in DC, capacitors are open circuit, okay? So you just replace them with open circuit. If there were no capacitors, so no change will happen. Then you do the DC analysis of the MOSFET, okay? Then we find ID and we make sure that the MOSFET is in saturation. Then, after we made sure, we go to the AC analysis. In the AC analysis, we remove all the DC sources. The same method. Voltage sources will be short, current sources open. The capacitors will be short circuit now. In DC, capacitors are open circuit. In AC, they are short circuit. So replace them with wires. And then we replace the MOSFET with either one of those models that I told you. I recommend you to replace it with this model. And the circuit parameters in the small signal model are obtained based on the value of ID and basically GM that you found. So if you saw a circuit like this, for example, that you wanted to analyze, and that you had capacitors involved, okay, in the DC analysis, you just consider these circuits to be open circuit. So your DC model will look like this one. Look, because I just opened the capacitors. Let's go back here. Look, this one will be gone. This one will be gone. This one will be gone. So what will be left will be this branch, this branch, this branch. And you remember I told you, since gate is not drawing any current, the current is not going to be divided between this 100 and the rest of the circuit. So whatever current is coming to this 1K resistor will go all simply to the drain of the MOSFET and will come down here to the source. So if you want to write an equation, simply say 10 minus ID times 1K minus VDS minus 2ID, because the current in the source and in the drain are equals 0. As simple as that. Also here, since the drain and the source are connected to each other using this resistor, and this resistor we know that it's not drawing any current, the voltage here and here are equal. So the VD equals VG. So VDS equals to VGS. Interesting, right? And we know that VDS is basically just add these two IDs together. It's going to be 10 minus 3 ID minus VDS equals 0. So VDS will be 10 minus 3 ID. So also VGS will be 10 minus 3 ID. So when we combine them with the formula that we have, ID, remember when we're in the saturation, ID is VGS minus K W over L, VGS minus VT square. So the even W over L, since it was a constant here, we put everything in 1K, okay? So we know ID is K VGS minus VT square. Also we know VGS is 10 minus 3 ID. And we have, look, in the problem, K is given to us, VT is given to us, right? So we have like two equations, two unknowns, like kind of here, right? Then what I did, we replaced in this equation, you replaced ID with K VGS minus VT square. Then you will find VGS to be 4.2 volts, or because you will end up having a second order equation, you will find two answers for the VGS. So this one is not valid in this case. If VGS is minus 1, it's in the cutoff mode, so it's not valid. So our answer is going to be valid. VGS is, because our threshold is 2. We know that VGS has to be greater than the threshold, right? So when VGS is 4.2, we actually confirm that the MOSFET is in the saturation mode. Then you can find GM as using the formula that I had given you. You can find GM, which is going to be 1.76 here. So I let the AC analysis of this problem to you. I leave it to you, and then I will show you the solution later on, okay? But look, some people, if they wanna analyze this more accurately, some people, they also, in this model, they also add a resistor in parallel with this current source, and they call it RO. Okay, RO. The value of the RO is found using this formula, 1 over lambda k VGS minus VT. That's why here in the problem a lambda is given, but we ignore it. As far as we're concerned, we ignore this one, so forget about it. But in this solution, to have a completely accurate solution, we have considered this to be there, this R0. So then I want you to continue this problem. I just show you the shape in the AC mode now. Look here what I have done. I have replaced the capacitors with short circuit now, right? And I have eliminated the DC sources. So the circuit is gonna look like this. Look, there used to be a resistor here parallel with the capacitor. Look at the original shape. There used to be a resistor parallel to capacitor. When we were doing DC analysis, we replaced this with open circuit, so we only ended up having the resistor. But when we do AC analysis, we will end up having a short circuit only, because it's going to be a short circuit parallel with the resistor, so it's going to be short circuited basically. So we're just going to have the wire here, and here this resistor is going to exist now. Before it was not there. And now we see the AC source. Before we could not even see the AC source because it was bypassed by a capacitor that was placed here. So this is a new our new shape. And then when we replaced the transistor, the MOSFET, with this pi model, I said in this case I have even considered the RO. But you can tell now that why we can, with a good approximation, we can eliminate it. This is usually this RO turn out to be a value that removing it is not gonna hurt us. But in this case, we have considered it. We found it over there. We found the RO turned out to be 103 kilo ohm. We considered it here to be there. But and this is the model. Look, the VGS, the GM VGS, because we found GM to be 1.76, and the resistor between the ground, between the gate and the drain, and then these two resistors. One of them is both of them are at the drain actually, and since the DC sources that they were connected here are going to be grounded, they're both of them are grounded. So this is the circuit that now we have to analyze, which is actually not too hard to analyze it. So take a look at what happened over here. As I said, I want you to do it yourselves, okay? But you have a glimpse of the simple circuit analysis here that we have, as you see, between the gate and the drain. There is 100K. So as you remember, the gate here is not going to draw any current. So this current and this current are the same, okay? So this I1 comes here and it's going to be divided into 4 branches. This, and this. This branch we know, right? It's going to be 1.76 VGS. And VGS is the voltage of V in. This branch is going to be V in, V out. Look, imagine here at the drain we have the V out, here we have the V in. So this branch is going to be V out over 103. This one is going to be V out over 1. This one is going to be V out over 3. That's why I1 equals to 1.76 VGS plus V out over 1 plus V out over 3 plus V out over 103. So it will be 1.76 V in, because VGS and V in are equal, plus 1.334 V out. Okay? We also know that, look, the both sides of this 100K, one side is V in, one side is V out. And the current that is passing through that is I in. So V in minus V out over 100K will give us I in, right? Or I1. So I1 is V in minus V out over 100. And also we know that I1 is 1.76 V in plus 334 V out. So forget about I1. We know that this part 1.76 V in plus 1.334 V out equals to V in minus V out over 100. So multiply 100 by this, so V in minus V out will be 176 V in plus 133.4 V out. And then you can find the gain easily. Just take the common factor from V in and V out. V out over V in will be minus 175 over 134.4. So it's going to be minus 1.31. Pretty small gain, but it's okay. But now I have actually an exercise for you. Redo this AC analysis, because now we did it together. Just in this time, remove this 103. Just use the model that we use, this model. Don't use the RO. And I want you to see how close the answer is to this one. This way you will make sure that, okay, it's not a big deal to remove this RO. Thank you very, very much. It was the last topic of our course. I hope you have enjoyed these online sessions, and I hope that you learned something during this pandemic time, and I really had a pleasure to have you, and wish you all the best, and wish you and all your families to be safe and sound. Have fun, take care, enjoy the rest of your days and nights, and see you soon. So come up with your questions to class. Bye bye.